Everything we know has an end. Our own lives are fleeting. The great empires of history rise and fall. Our planet, the Earth, will one day be sterilized and then swallowed by our dying sun. The sun itself will eventually exhaust its fuel and fade into a cold, dark cinder. Even the brilliant, sprawling galaxies will, over unimaginable timescales, dissolve into darkness. But what about the whole thing? What about the universe itself? Does it have an end? And if so, how will it all play out? Will it end in a fiery collapse, a big crunch? Or will it end in a cold, eternal expansion? For centuries, this has been one of the ultimate questions in science and philosophy. But now, thanks to our growing understanding of cosmology, we are beginning to piece together a plausible timeline for the end of everything. And a recent, surprisingly specific prediction has given us a new date for our cosmic calendar. A team of physicists has calculated that in just 22 billion years, the universe as we know it, this grand, beautiful cosmic web of galaxies and clusters, will begin to dissolve, its structures torn apart by the accelerating expansion of space. This isn't the final, ultimate end of everything. It is, in fact, just the very beginning of the end. It's the first step on the long, dark, and inevitable road to the ultimate fate of the cosmos. A final, chilling state of perfect, eternal equilibrium known as the heat, death of the universe. The law of cosmic decay. To understand the ultimate fate of the universe, you don't need to start with black holes or quantum physics. You need to start with something much more familiar, a hot cup of coffee. Imagine you place a freshly brewed, steaming hot cup of coffee on a table in a cool room. What happens? The heat from the coffee, which is a form of concentrated, ordered energy, will naturally and inevitably flow outwards, warming up the surrounding air. The coffee gets colder, and the room gets infinitesimally warmer. This process continues until the coffee and the room have reached the exact same temperature. At that point, the system is in a state of thermal equilibrium. The total amount of energy is still the same, but it's now been so evenly distributed that it's become useless. You can't use that lukewarm, room temperature energy to do anything useful, like power an engine. The system has reached a state of maximum disorder. This simple, everyday observation is an example of the most powerful and fundamental law in all of physics, the second law of thermodynamics. The first law is the famous one. Energy cannot be created or destroyed, only changed from one form to another. The total amount of energy in a closed system, like the universe, is constant. But the second law is the one that governs the destiny of that energy. It states that in any closed system, the total amount of entropy will always increase over time. Entropy is, in simple terms, a measure of disorder, randomness, or uselessness. The hot coffee is a low entropy state, ordered, useful energy. The lukewarm room is a high entropy state, disordered, useless energy. The second law is the one-way street of physics. It is the arrow of time. Coffee always cools down. It never spontaneously heats up by sucking warmth out of the room. Scrambled eggs don't unscramble. Things fall apart. This is the unshakable rule that governs everything. The heat death of the universe is simply the logical, ultimate conclusion of applying the second law of thermodynamics to the entire cosmos. The universe itself began in a very special, highly ordered, low entropy state, the Big Bang. It was an incredibly hot, dense, and remarkably uniform singularity of pure, useful energy. For the past 13.8 billion years, the universe has been running down, following the second law just like that cup of coffee. It has been relentlessly converting its ordered, useful energy, like the immense potential energy stored in clouds of hydrogen gas, into disordered, less useful forms, like the waste heat and light radiated by stars. The heat death is the predicted final state, a future where this process is finally complete. It's a future where all the matter and energy in the universe has been so evenly and thinly distributed that the temperature is the same everywhere, just a tiny fraction of a degree above absolute zero. In this state of perfect, maximum entropy, no work can be done. No temperature differences exist to drive any processes. No stars can shine. No planets can form, no chemical reactions can occur, and no life as we know it can possibly exist. It is a state of perfect, eternal, and unchanging darkness and silence. It is the ultimate end. The era of fading stars. The journey to this final cold end is an impossibly long one, divided into a series of distinct cosmological eras. And the first major milestone on that journey is the specific prediction that gives our story its title. The end of structure, 22 billion years from now. To understand this prediction, we need to introduce the biggest and most mysterious player in modern cosmology: dark energy. In the late 1990s, astronomers made the shocking discovery that the expansion of the universe is not slowing down as everyone had expected. It is accelerating. There is a mysterious force, a kind of anti-gravity built into the fabric of space-time itself, that is pushing everything apart at an ever-increasing rate. We don't know what this dark energy is, but it makes up about 70% of the entire universe. A team of physicists, including theoretical physicist Matt Kaplan, recently ran a series of sophisticated simulations to figure out what this acceleration means for the future of cosmic structures. Their prediction is stark. The accelerated expansion is like a rising tide. For now, the force of gravity is strong enough to hold together structures like our own galaxy and even our local group of galaxies. But on larger scales, dark energy is already winning. Their calculations predict that in approximately 22 billion years, the expansion will have accelerated to such a degree that all the galaxy clusters and superclusters that are not already gravitationally bound to our own supercluster will be pushed beyond our cosmic event horizon. This is a point of no return. These distant galaxies will be receding from us at a speed faster than the speed of light. This doesn't violate Einstein's theory, because it's space itself that is expanding, but it means that the light emitted by those galaxies after that point can never ever reach us. They will wink out of our sky one by one, as if they never existed. The vast, interconnected cosmic web that we see today will be gone. The universe will become a collection of lonely, isolated island galaxies, each one trapped in its own observable bubble, unaware that any other galaxies even exist. This is the end of structure the prediction refers to. It is the beginning of the universe's ultimate isolation. The stelliferous era, now to 100 trillion years from now. Even within these isolated island galaxies, for a very long time, things will continue much as they do now. This is the stelliferous era, or the age of stars, the era we are currently living in. For trillions of years to come, stars will continue to be born from collapsing clouds of gas and dust. They will shine for millions or billions of years by fusing hydrogen into helium, and then they will die, some in spectacular supernova explosions, others by quietly fading away. But the fuel for star formation, the vast clouds of interstellar hydrogen gas, is a finite resource. Each generation of stars locks up more and more of this material into stellar remnants and heavy elements. Over an immense timescale, the gas will be used up. The great glowing nebulae will fade. Star birth will become rarer and rarer, until eventually it stops altogether. The last stars to be born in the universe will be the smallest and most frugal ones, red dwarfs. These tiny, cool, and incredibly dim stars have much less mass than our sun, so they burn through their hydrogen fuel at an almost unbelievably slow rate. A red dwarf can live not for billions, but for tens of trillions of years. For a timescale that is thousands of times longer than the current age of the universe, these faint red suns will be the only sources of light in an otherwise dark and empty cosmos. But even their lifespans are finite. Sometime around the year 100 trillion, the very last red dwarf will finally exhaust its fuel. Its fusion will cease and it will slowly cool down, fading from a dim red to a dull black. With the death of the last star, the stelliferous era will come to an end. The universe will go dark, forever. The degenerate era, 100 trillion to 1040 years from now. Welcome to the degenerate era. The universe is now a cold, dark, and silent graveyard of stellar corpses. The only major objects that remain are the dead remnants of the stars that once shone so brightly. white dwarfs, the incredibly dense Earth-sized cores of sun-like stars. Neutron stars, the even denser, city-sized remnants of supernovae. Black holes, the final victory of gravity, left over from the death of the most massive stars. For a timescale that is almost beyond human comprehension, these degenerate objects will drift through the darkness, occasionally colliding, but mostly just slowly cooling towards absolute zero. But the universe is not done with them yet. Two strange and wonderful processes, one predicted and one proven, will ensure their ultimate demise. The first is a speculative but widely accepted idea from particle physics called proton decay. Our current theories suggest that protons, the building blocks of all atomic matter, are not fundamentally stable. Grand unified theories predict that over an almost impossibly long timescale, protons will eventually decay into a spray of lighter, more stable particles like positrons and photons. The predicted half-life of a proton is at least 10^34 years, a number so large it is effectively infinite from a human perspective. But on the timescales of the degenerate era, it becomes relevant. If proton decay is real, then all the matter that we know and love will slowly and steadily evaporate. The white dwarfs and neutron stars, the planets and asteroids, every last atom of hydrogen, carbon, and iron will eventually decay. Over trillions of years, these stellar corpses will simply dissolve into a diffuse, low-energy bath of radiation and elementary particles. The age of black holes. If proton decay doesn't happen, or if it's not the whole story, the universe has another, even more patient method of housecleaning. The next era is defined by the absolute and final dominance of gravity. Welcome to the black hole era, the reign of black holes, 1040 to 1000 years from now. Imagine a future so distant that the concept of a trillion years feels like a fleeting instant. The degenerate era has ended. All normal matter has either decayed or been swallowed. The only significant structured objects left in the entire universe are black holes. The small stellar mass black holes left over from dead stars will still be drifting through the void. And at the center of what was once each galaxy, the supermassive black holes will have slowly consumed any remaining stars and gas, growing to gargantuan sizes. The universe at this point is a near-perfect vacuum, a vast cold and dark emptiness, containing only an achingly dilute gas of photons and leptons, like electrons, and these silent gravitational behemoths. Even the galaxies themselves will have dissolved. Over these immense timescales, the complex gravitational interactions between the stellar remnants will have caused the galaxies to relax, either flinging their dead stars into the intergalactic void or sending them on a final one-way journey into the central supermassive black hole. The universe is a blank canvas, dotted with only the blackest of all possible paint, but even the black holes are not eternal. The final act of destruction, and the last interesting physical process to occur in the universe's history, comes from one of the most brilliant discoveries of the 20th century: Hawking radiation. In 1974, the physicist Stephen Hawking, combining the laws of general relativity with quantum mechanics, made a stunning discovery. Black holes are not, as was previously thought, perfectly black. They have a temperature, and they glow. Due to the strange rules of quantum field theory, the empty vacuum of space is actually a bubbling, frothing sea of virtual particles. Particle-antiparticle pairs are constantly popping into existence out of nothing, existing for a fleeting moment, and then annihilating each other. Hawking realized that right at the edge of a black hole's event horizon, a strange thing can happen. A pair of virtual particles can pop into existence, and one of them can fall into the black hole while the other one escapes into space. To a distant observer, it would look as though the black hole had just emitted a particle. Because of the conservation of energy, the black hole must pay for the creation of this escaping particle by losing a tiny amount of its own mass energy. The net effect is that the black hole will slowly, particle by particle, evaporate. This process of evaporation via Hawking radiation is incredibly, fantastically slow for large black holes. The rate of radiation is inversely proportional to the black hole's mass. A black hole with the mass of our Sun would take an estimated 10⁻⁻⁶7 years to completely evaporate. A supermassive black hole at the center of a galaxy, with 1 billion times the mass of our Sun, could take up to 10⁻100 years to disappear. That number, 10 to the power of 100, is called a googol. It is a number so vast that it is physically impossible to write it out in standard notation. If every single proton, neutron, and electron in the entire observable universe were its own, separate universe, and each of those universes lived for the entire current age of our universe, the total amount of time elapsed would still be an insignificant fraction of a googol years. The black hole era is the longest, darkest, and quietest period in the universe's history, but it will have a final, spectacular end. As a black hole radiates away its mass, it gets smaller. And as it gets smaller, its temperature increases and it radiates away mass even faster. This creates a runaway process. In the very last second of its life, a black hole, having shrunk to a microscopic size, will release all of its remaining energy in a final, weak but detectable flash of high-energy gamma rays. For a googol years, the silent dark universe will be punctuated by these last, lonely pops, as the final organized structures of matter and energy in the cosmos disappear forever. The eternal darkness. With the evaporation of the very last black hole, the universe enters its final, ultimate state. Welcome to the dark era, the final state, beyond 10⁻100 years from now. The last black hole is gone. What is left? The universe is now a vast, cold, and achingly dilute soup of the most stable fundamental particles. It will be composed almost entirely of photons, with incredibly long, low-energy wavelengths, neutrinos, and a sparse scattering of electrons and their antimatter counterparts, positrons, all drifting aimlessly and ever farther apart in a perpetually expanding void. This is the state of maximum entropy. All the useful, ordered energy that was born in the fires of the Big Bang has now been converted into useless, disordered, low-grade waste heat. The temperature of the universe will be infinitesimally, but not quite, at absolute zero. There are no structures. There are no processes. There are no temperature differences left to drive any kind of work or change. Time itself, in any meaningful sense, ceases to have a direction. The arrow of time that we experience is driven by the relentless increase of entropy. But in a universe that has already reached its maximum possible entropy, the arrow has nowhere left to point. Change ceases. Nothing happens. And nothing will ever happen again. This is the heat death of the universe. It's not a fiery, dramatic end, but an infinitely cold, quiet, and final one. It is a universe that is, for all intents and purposes, dead. Is there any possible hope? Is there a loophole in this bleak forecast? On the furthest fringes of theoretical physics, there are a few speculative glimmers. Over an almost infinite amount of time, a timescale known as a Poincaré recurrence time that makes even a googol years look short, it is theoretically possible that a random quantum fluctuation could by sheer chance create a new complex, low-entropy state. Could a new Boltzmann brain, a self-aware consciousness, or even a new Big Bang spontaneously fluctuate into existence out of the quantum foam? It's a wildly speculative idea, but it's not a complete impossibility. Other, even more speculative models, like cyclic universe theories, propose that our universe might go through endless cycles of expansion and collapse, or that dark energy itself might change its nature in the far future, triggering a new beginning. But based on the physics we know today, the journey to the heat death is the ultimate story of cosmic evolution. The prediction of an end of structure in a mere 22 billion years is just the first nearby signpost on this impossibly long and dark road. From the final, lonely flicker of the last red dwarf to the slow, patient evaporation of the last supermassive black hole, the universe is relentlessly marching towards a state of perfect, silent equilibrium. It's a sobering and humbling vision of the future, a reminder that even the cosmos itself is mortal. But it also highlights the incredible, precious, and fleeting nature of our present moment. We are living in the vibrant, star-lit, chaotic youth of the universe, a brief and glorious flicker of warmth and complexity before the beginning of the long, cold, and eternal night.